Hello there. During this session I'm going to be talking about time dilation. That is the seemingly different passage of time dependent on if you are travelling at a velocity or not. Okay. So this is what we're going to be looking at today, and how it occurs and some interesting consequences. So let's start off with getting some definitions about time. So we're going to start off by using time as measured by a light clock. Okay, so a light clock is an imaginary device for measuring time in an absolute way. It does not have any moving parts, but simply relies on a pulse of light being continuously reflected backwards and forwards between two mirrors. Okay, because the speed of light is an absolute value, that means it should take the same amount of time for this process to take place every time. A proper clock is the time interval measured in a frame of reference between two events which occur at the same point in space. Okay, so that means that your proper clock is the clock which is traveling with you. Okay, it's in the same frame of reference. That's important. And now let's just show, I'm going to show kind of a quick simulation which distinguishes between some of the issues of a absolute time from a proper clock and a clock which is not travelling in your frame of reference. So let me just click onto here. Okay. So what we've got is here a situation with Jack and Jill. Jack is at rest and Jill is at this moment in time travelling at a velocity of 0 meters per second. So that means if we have here, if I press play, what we can see is our clocks are completely in sync with each other. Now what I'm going to do is I'm going to do exactly the same thing, but we're going to have Jill moving at half the speed of light. Okay. Now in this situation you're going to see that things are perceived differently. So I'm going to start again, and we're going to see what Jack's clock reads, and we're going to see what Jill's clock reads. Now what we've got here, okay, Jill's clock, okay, from Jill's perspective, she is travelling at a constant velocity, but has no idea that Jack's perceiving the distance travelled by the light as different. So Jill's clock to her reads 10 seconds. However, Jack's clock reads 11.6 seconds. And this is for the distance, for the time taken for the light to travel to the mirror and back again. So we can see that there's an issue here. The round trip, although perceived by Jack, or perceived by Jill to take 10 seconds still, Jack measures Jill's situations taking slightly longer than that. So we have an issue here with time. So let me take us through this in a little bit more detail. So what we have here is we can see that if we're travelling light from one end and bouncing off the other end, what's that going to be is a distance of 2d. Now that's going to take, that distance is going to be equal to the speed of light multiplied by the time it takes. So therefore the change in time is twice the distance divided by the speed of light. And this is proper time, okay? So it's perceived, it is the rest frame of the event, okay? Nothing seems to be moving. So this gives our proper time. And this is the time of the observer as measured by the light clock when the light clock is at rest to the observer. Now I've got a situation where I have a moving light clock. Now with my moving light clock, we can see, as we see beforehand, my little diagram shows that although that the observer where the light clock is at rest still this taking 2 seconds. The person who sees this due to moving thinks it took 2.31 seconds. So let's look at how we can derive these numbers. First of all, the length travelled is going to be the velocity of the other frame of reference multiplied by the change in time. Distance is still the same, but now I need to work out the length of the distance the light travels from the perception of the observer who is not moving. So what we have here is that velocity times time divided by 2 gives me this distance here. Okay. Imagine that the light bounces back again, so therefore the total distance here is the velocity times by the change in time, but the divided by 2 gives me half of that distance. So from beforehand, and now I'm going to be using a little bit of Pythagoras, I can work out that d squared plus velocity times the change in time divided by 2 squared, the square root of that is going to be the distance travelled by the light along this hypotenuse. Now I've got to multiply that by 2 because remember it has to bounce back again, and that should be equal to the speed of light times the time taken. So if I rearrange this for the time taken, it gives me this new formula, and I then recognize that 2d divided by c gives me a value for the proper time. So this is the time as perceived by someone who's not moving. So now I've got a way of calculating the time which was perceived using the velocity of the frame of reference and the proper time as a reference, as values here. So velocity of the frame of reference. And so here's a typical IB question, and what it does is it's basically leading you through a derivation of this idea. So pause, think back, try and answer this question. It would take you, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 marks here. So we're talking about probably about 10 minutes, maybe a little bit longer. And when you come back, I'll take you through the answers. So the mark scheme says this, and as you can see, each step is basically looking for a derivation of the time dilation which we've already identified. Okay. So that's one thing the IB may ask you for. Here's another example question. Alpha Centauri is 4.3 light years from Earth. It takes a light 4.3 years to travel from Earth to Alpha Centauri. How long would people on Earth think it takes for a spaceship traveling at 0.95 c to reach Alpha Centauri? Well, it'll just be distance divided by velocity. So 4.3 divided by 0.95 gives me 4.5 years. How long do people on the ship think it takes? Well, their perception is different. People on the ship have proper time. They see Earth leave and Alpha Centauri arrive. So what happens here is using the time dilation formula and rearranging for their proper time. Their proper time is going to be 1.4 years. So there's some example of time dilation. Hopefully that'll be useful for you. The IB requires us to sketch and annotate a graph showing the variation with relative velocity of the Lorentz factor. Now let me just identify what the Lorentz factor is. It's something which we've shown you, but I haven't named it as such. So previously I said time dilation can be worked out using this formula. As it happens, the IB breaks it down and simplifies this a little bit. And they say that they produce this factor which impacts the change in time, and this factor here is known as the Lorentz factor, and therefore if you multiply perceived time multiplied by the Lorentz factor, then what you're going to get is the perceived time. Now if we look carefully at this Lorentz factor and put some numbers into it, it becomes quite interesting. So if there is a value for v which is very small compared to the speed of light, well, what happens then? It just becomes, the Lorentz factor becomes a value of 1, and the observed time and is equal to the time which is per proper time by the person moving. When we approach the speed of light, this factor becomes larger, and this can be seen graphically. So when plotted graphically, we have a graph a little bit like this. So time dilation, when we're talking about values, smaller values, is fairly insignificant. The closer we get to the speed of light, the greater the time dilation is. And that's the key feature we need to think about here. So this is a graph showing the amount of time dilation compared to the fraction of the speed of light. So let's recap on time dilation. These are the formulas here which you get given by the IB. You've got to remember that the Lorentz factor is always 1 or greater if time is greater than time on the spaceship. So that's one thing to recognize. The time interval, or proper time, is measured by a clock in your own reference frame, whilst the change in t, delta t, is the interval time measured by an observer moving relative to that clock. And that is the symbol for the Lorentz factor. So these are the key things about time dilation. Next lesson we're going to talk about length contraction.